Statistics is always concerned about why and how something or someone is different. The variance and standard deviation measures the extent of differences in a given variable. The degree of inequality for a given variable is measured by the standard deviation relative to the mean. Large standard deviation suggests greater inequality or disparity for a given variable. Small standard deviation suggests that the degree of inequality or disparity for a given variable is smaller, minimal, or even negligent. Standard deviations of 0 indicate that all individuals have the same value for that variable. For example, if the entire 8th grade class weighs 100 pounds, it would be impossible to test the impact of weight on height because there will be no frame of reference as the data for other weights are not available. Because of that, we cannot draw conclusions about the impact of weight on height, and the statistical program would give us an error message if we try to do so. As measures of inequality or disparities, standard deviation and variance paints the best or the worst picture of a given society. Or put it this way, as measures of inequality or disparities, standard deviation and variance paints the best or the worst of a variable in our data. If you square the standard deviation, you get the variance. Or put it differently, if you take the square root of the variance, you get the standard deviation. If you square the standard deviation, you get the variance. Or put it differently, if you take the square root of the variance, you get the standard deviation. When you multiply the standard deviation by itself, it intensifies large values. For instance, the square of 1 is 1, the square of 2 is 4, the square of 3 is 9, the square of 4 is 16, and so on. As you can see, the value gets larger as you progress from 1 to 2, and then to 3, and so on. At times, the standard deviation makes more intuitive sense. Thus, the purpose of using the standard deviation is to keep values close to the mean. As you can see from the formula, the numerator x minus x bar indicates how far the data point is from the center of the mean. At other times, the variance makes more intuitive sense than the standard deviation. This is because taking the sums of square deviations gives us a 0. So, we will use the variance when we want to measure the sum of squares. We square the standard deviation so that it becomes the variance because we want the negative and positive dispersions to have a role in the measurement scheme. One intuitive explanation is that the n minus 1 in lieu of n in the denominator is a degrees of freedom adjustment stemming from the fact that we are using the sample mean rather than the population mean in our calculation for the sample variance. Using n minus 1 is useful for scale measurement. To prove that you need to have n minus 1 in the denominator requires basic familiarity with the expectation operator. You add and subtract the true population mean inside the brackets of the squared term, rearrange them, then expand the square before bringing through the sigma operator.